Okay, so welcome back after the break. So the rest of this lecture we will prove some facts about Dulmage-Mendelsohn barriers. We'll start with, Lemma 5.2 is a DIY. Does everybody see that? So let's just recall what a Dulmage-Mendelsohn barrier is. So we are defining a Dulmage-Mendelsohn barrier for matchable graphs. We want the core to be matching covered, right? Everybody remembers the core. You throw away the even components, you throw away all the edges that have both ends in the barrier, and you shrink every odd component into a single vertex, right? So you get a bipartite graph, that is clear. It is also clear that it is a bipartite matchable graph because the original graph is matchable. So in fact, if you take any perfect matching of the original graph and you restrict it to this core, you have a perfect matching of the core. Therefore, the core is always bipartite and matchable. But it need not be matching covered. So the first property we want for the core is for it to be matching covered. And the second property we want is similar to a property we get for free for maximal barriers, which is that every odd component is actually critical, also known as factor critical or hypomatchable. Yeah. So because we want the second property, it is natural that if you want to show the existence of a Dulmage-Mendelsohn barrier, you should probably start with a maximal barrier. You'll get the second property for free if you are careful. Right? Of course, the maximal barrier may not be a Dulmage-Mendelsohn barrier. That's an issue. So what we'll actually prove is the following statement, that inside every maximal barrier sits a Dulmage-Mendelsohn barrier. And additionally, the odd components after deleting this Dulmage-Mendelsohn barrier are also components after deleting the original maximal barrier. So if we show the existence of a Dulmage-Mendelsohn barrier with that property, then we will get the second property for free. Yeah? Everybody sees this? Right? So therefore we will start with a maximal barrier and we will show that it includes a Dulmage-Mendelsohn barrier with this additional property. Right? And if we do that, then we are good. Yeah. Questions, concerns, all good? Okay. So that's the first thing we're going to prove, Lemma 5.4. And I hope everybody sees this. For a Dulmage-Mendelsohn barrier, every edge of the core is matchable in the original graph. That is not true for a general barrier. If you take an edge of the core, that may not be matchable in the original graph. But because of Dulmage-Mendelsohn barrier, you get the core to be matching covered. That is why you get this property that every edge of the core is actually a matchable edge in the original graph. Everybody sees that? Right? Okay. So hopefully this one you have all done. It was a DIY. So this is done. It's actually an exercise in Lucceshi-Murty, so it might be an exercise for you also on one of the future assignments, I don't know. So we will not do this, we will focus on 5.4. Okay. So let's take any maximal barrier. So let me just draw a maximal barrier. Supposing this is my maximal barrier, B star. Of course, I can draw the odd components, even components, etc. But instead of that, I will just draw the core. Yeah, I'll just draw the core. So that just means for every odd component, we get a single vertex. And we'll call this set naturally A star. This is a set of vertices of the other color class, and each of them corresponds to an odd component of G minus B star. Yeah. So this is the core. If the core is matching covered for some reason, then we are done. Then this is a Dulmage-Mendelsohn barrier because we got the core to be matching covered, and it is a maximal barrier. So all the odd components are actually going to be factor critical. So we get the second property of Dulmage-Mendelsohn barrier, And of course, B is equal to B star. So every odd component of G minus B star is an odd component of G minus B. You are done, right? So if this happens to be Dulmage-Mendelsohn barrier, then we are done. Or in other words, if this core is the core is matching covered, then we are done. So the interesting case is when the core is not matching covered, right?
B star is maximal value.
Yes, B star is maximal value. Yes, B star is maximal value. Yeah. So let's just make a note of this. If the core with respect to B star is matching covered, then done. Set B to be equal to B star and observe that everything works. So the interesting case is only when B star is not matching covered. But we know it is a bipartite matchable graph. Yeah. However, this graph is bipartite is clear, but more importantly in this context, it is a matchable graph. So, therefore we can do something. We can use one of your assignment 1 exercises and finish the proof from here. So TIY, I'll come and talk to you. Okay. So TIY, what is this exercise? Exercise 2.3.2, is it? Something like that.
Yeah.
2.3.2. Okay, let me know if you have figured it out. Make a drawing, show me the drawing, and then we are done. Okay, you have a drawing? Yeah. Okay, what else?
apart from this S and this big one, this is the even number of having even number of faces. So if it is connected, then what are doing? So what will be because what is the B? Here, what is the B star? Yeah, this is B star. This is my B star, and now that S is completely B. No, this is a problem.
These are in the second statement. Each odd component of G minus B is an odd component of G minus B star.
Each odd component of
G minus B is an odd component of G minus B star. That doesn't work. Second condition. Remember the second condition was each odd component of G minus B is an odd component of G minus B structure. I could write it. So how did you choose this set? But now my question is, what do you do the second condition? Each odd component of G minus B. G minus B is this. G minus B. This is B. Each odd component of G minus B to be an odd component of G minus B star. So most of you, so all of you are sort of trying the right approach. You are applying this exercise 2.3.2, which says that there is a subset in, you can choose any color class. Now there is a subset in that color class, so that the graph induced by that set and its neighborhood is a bipartite matching covered graph. The question is, which set do you apply that to? Do you apply that to B star or do you apply that to A star? That's the part you have to think about. Because if you apply it to the wrong set, it doesn't work. Remember this condition. This condition is very important. Each odd component of G minus B is also an odd component of G minus B star. That is also a condition you need, and that condition actually helps a lot to figure out where you should apply. So pretty much everybody tried this. You basically found a set. The main point is, do you take S to be subset of B star or do you take S to be subset of A star? And then how do you define the set B? Yeah? Everybody sees the point? Yeah, shall I write it down? Yeah? So, basically you want to choose a set S here. There exists a set that is a subset of A star, such that the neighborhood will be the same cardinality, and in fact the graph induced by S and the neighborhood of S will be a bipartite matching covered graph. So I may conveniently draw n of S to be like this. What does this mean? Where do all the edges go? The edges go like this, the edges go like this, and the edges go like this. So when I delete this set, these are still going to be odd components, and they are also odd components of the original G minus B star. So this is your B. Now it works. Now everything goes through. You got a Dulmage-Mendelsohn barrier. Why? Because what is the core? The core is simply all of these are odd components. I got 3 odd components, so there cannot be more than 3 odd components. The original graph is matchable. So therefore I just shrink all of these into single vertices. I throw away everything else, it doesn't matter. And I throw away all the edges here. So core is matching covered because we chose S using exercise 2.3.2. Right? And also we get the second point. Every component of G minus B, these creatures, they are also odd components of G minus B star. Right? So this is basically what works. Right? So let's just write it down really quick. In fact, I'll write it more generally. I don't even need this is matching covered, not matching covered. There exists a subset S of A star. This is not going to be empty, of course, such that the graph H induced by S union the neighborhood of S in this graph, of course, is matching covered. Now let B be n of S and observe that everything goes through. If the graph was matching covered, then your S would just be equal to A star and you would not have to do anything. So actually in reality you don't need all of that. Right? Questions, concerns? Yeah. And the reason we call this a Dulmage-Mendelsohn barrier is because essentially this part that we are using is what gives you the Dulmage-Mendelsohn decomposition, which is exercise 2.3.3, I think. So you get the entire Dulmage-Mendelsohn decomposition by just applying 2.3.2 and then proceeding by induction. So I gave a part of the assignment solution. Okay. Okay, questions, concerns, all good? Yeah? Okay. So that's that. And now we are left to prove the last statement. Right? This is if you see this for the first time, it looks strange, but you should think of this in context of 5.1. Right? In context of 5.1, we delete the two vertices U and V, and we got a matchable graph. That's the setting in which this will be applied. Of course, here we'll take G to be a matchable graph. Right? And we have this even cut with the property that no edge in that cut is matchable. Right? And both the shores are actually connected. Both the shores induce connected subgraphs, but no edge in the cut is matchable. That implies that both the shores are actually even, and in fact they are matchable. Right? Then what we want to show is that there is a Dulmage-Mendelsohn barrier. Let's just make a drawing. So yeah, maybe I'll erase everything. Is it okay? This part. Okay, So what we want is something like this. We have a this is a matchable graph. This is our cut partial of x, and edges in this cut, they are not matchable in the graph. Therefore, the graph induced by x and the graph induced by x bar, they are both matchable. In particular, this is an even cut, unlike most cases when we look at odd cuts, right? What we want to show is that the graph G has a Dulmage-Mendelsohn barrier. So what we want to show, I'll draw that part in orange. We want that barrier to live in one shore. Dulmage-Mendelsohn barrier B. We want the entire barrier to be living in one shore, one of the shores. And we want the vertex sets of all odd components to be on the same shore. Right? All odd components, their vertex sets should be living in the same shore. This is what we want. Yeah? Statement clear? Okay. But we will use the previous lemma statement which I conveniently erased. We know that in any maximal barrier there is a Dulmage-Mendelsohn barrier. Okay, so let's try. These two graphs are connected also. Remember that these are connected. Connected is already given to us. But the graph G itself need not be connected. We don't know whether the graph G itself is connected. So the cut could actually be empty, in which case it will be disconnected. Otherwise it will be connected. So let's make another drawing because that is what we want. This is what we have, mostly an empty slate. Okay, that's what we have. And let's remind ourselves that these two graphs are connected and matchable. Yeah, okay. So we'll consider two cases. Either the cut is empty or the cut is not empty. Yeah, cut is empty should be easy, but let's do it anyways. Let's suppose the cut is empty. This is very easy. The reason we are going to allow this case is because in the main proof, this case could appear. Right? When you delete the two vertices u and v, after applying that lemma 5.1, you could get a disconnected graph. So therefore, we are going to allow this situation. Yeah. So we have a connected matchable graph here. We have a connected matchable graph here, and the cut is actually empty. So Ti by. If you figure it out, let me know, I'll come and talk to you. Yeah, everybody sees it? Yeah, this one is straightforward. Yeah. Most statements are easy once the graph is disconnected. Yeah. Right. So, okay, fine. So, we're all done, I guess. There's a Dulmage-Mendelsohn barrier in this graph. One way to see that is to take a maximal barrier, and inside a maximal barrier there lives a Dulmage-Mendelsohn barrier. So, you can directly take a Dulmage-Mendelsohn barrier. And because I took a Dulmage-Mendelsohn barrier in this graph, all the odd components are going to be here. And because the cut is empty, everything works out. The barrier is still a barrier. This is going to be a matchable connected graph. So all components here are actually even. In fact, this is a single connected graph. It's an even component. So when I look at the core, I just delete this fellow. The core with respect to this graph. Earlier we were looking at the core with respect to this graph. But now we are looking at core with respect to the big graph G. So we'll just throw away this part. And then we are just looking at the core with respect to the original graph, right? So the core is going to be matching covered, and each odd component, well, the barrier is living here, so the odd component is also going to live here. So everything is done, right? So this is easy. Yeah. Okay. So the interesting case is when the cut is non-empty. Fine. Okay, so now let's consider the interesting case. Now suppose that partial x is not empty. That means there is an edge in the cut. Let's draw one edge, u, v. Yeah. What do we know about this edge from the hypothesis? This edge is not matchable. Yeah. This edge is not matchable. When you see an unmatchable edge, what is the first thing you want to do with it in the context of what you're trying to prove here? Right. You have an unmatchable edge, and you want to take a barrier containing that edge, the two ends of that edge, to be more precise. Right. Then you want to take a barrier containing the two ends of that edge. Should we take any barrier, or should we take a more convenient barrier? Maximal, because you want to use the earlier lemma which had a maximal barrier. So we'll take a maximal barrier containing the two ends of this edge. There exists a barrier containing u and v in the graph G, and let B star denote a maximal such barrier. In other words, u and v belong to B star. Yeah. So we have a maximal barrier containing these two vertices, and but we want to show the existence of a Dulmage-Mendelsohn barrier. Right, that's what we want. Well, but then we know from the previous lemma that every maximal barrier contains a Dulmage-Mendelsohn barrier. So maybe we'll just apply that right? What else is there to do in life? By lemma 5.4, B star includes a Dulmage-Mendelsohn barrier. B could be equal to B star, we don't know, right? But includes a Dulmage-Mendelsohn barrier. Okay, good. So we'll now think about this barrier. We want to argue, so as you can see by the choice of notation, we want to argue that this B is the desired B, right? So we want to show that the barrier B itself lives in one shore. Either it is completely contained in the X shore or it is completely contained in the X bar shore. And once we show that, but we need not respect the order every time in life. We also want to argue that the odd components live in the same shore. Yeah. So these are the two things we need to show. We need to basically make this drawing either on this side or that side, right? Somehow. Okay. Let's see. What we will actually do, we will first deal with odd components. We will first show that every odd component, its vertex set, either completely lives on the X side or it completely lives on the X bar side. That is what we will first show. And that actually turns out to be very useful. In fact, let's suppose that happens. Can we finish the proof from there? That is one way to do things in life. Supposing I convince you that every odd component, I don't know where the barrier is. The barrier B could be completely here or there, I don't know. Or it could have some vertices from here or some vertices from there. In fact, B star we chose has a vertex in both sides, both shores. It contains U and V both. So B star actually spans, or I don't know spans. B star actually intersects both the shores, meets both the shores. B we don't know. Supposing I convince you that every odd component of G minus B lives in one of the two shores. So either it is completely contained in X or it's completely contained in X bar. Then can we finish the proof from there? Can we try to first think about that? Okay, let's see. So claim. Each odd component of G minus B is the vertex set. Vertex set of each odd component of G minus B is either a subset of X or of X bar. Let's suppose we assume this claim. Then can we finish the proof? Okay, so here's the TIY. Assume the claim and finish the proof. Okay. You have to use all the properties you have in life. Right, so let's see what all we have. We know that the core is matching covered. Maybe I should remind you of all the other things also. So core is matching covered. And if an edge in the core is matchable, then it is also matchable in the original graph. In this case, the core is actually matching covered. Therefore, every edge of the core is actually matchable in the original graph. Some odd components are living here, some odd components are living there. Let's make a drawing. Let's make a bad drawing. Drawing that we don't want. So what we don't want is some situation like this. So let's say I have 5 odd components. 2 are here, 3 are here. That means the barrier also has 5 vertices. I don't know how many vertices of the barrier are there. But some vertices could be here, some could be here, I don't know. Supposing the situation looks like this. Now see if you can figure out a contradiction. What we do know is that so we are assuming the claim. The claim is saying that every odd component is either here or there. Right? We don't know anything about the barrier. We have not made any statement about the barrier. But we want to show that this actually implies this. The whole barrier and all odd components live in one and the same shore. Yeah, maybe I'll also put vertices in the barrier. This doesn't look nice. I don't know. So if you convince yourself that the claim finishes the proof, then your next DIY is prove the claim. Anybody else? Assuming the claim, do you see the proof how to finish it? Yeah. Okay. Okay, anyone else? Right, exactly. So, yeah, basically the point is, the good thing about this claim is that it allows you to visualize the core in a very nice way. Because what is a core? Well, every vertex of the barrier is a vertex in the core. Yeah. So the vertices, of course, are either the vertex is either in X or in X bar. And every odd component of G minus B is a vertex in the core in the other color class. So because of this claim, I can basically visualize the entire core sitting nicely inside the graph with respect to this cut. Vertices of the barrier, some will be on the left, some could be on the right, I don't know. Some odd components could be on the left, some odd components could be on the right. But there is no odd component that looks like this, that meets the yellow line. That's good. So I can visualize the entire core here in a very nice way. And if the core actually has some vertices here and some there, because the core is matching covered, because it's a Dulmage-Mendelsohn barrier, that means there will be some edge of the core that meets the cut. But every edge of the core, because it is matching covered, is matchable in the original graph. But we know that edges of this cut are not matchable in the original graph by hypothesis. So therefore the entire core has to be either on the left side or on the right side. Right? The picture is actually easier to think of. Writing is maybe, well, anyways, you can all write it. You all have done SGT, you can write this out. Right? It's clear? Yeah? So basically the core being matching covered and no edges in this cut being matchable is basically what tells you that everything has to live in X or everything has to live in X bar. By everything I am referring to the barrier and the odd components. Yeah? Fine. So all we need to prove now is the claim. Do you all agree? If we prove the claim, we are done. Yeah? Okay. Suppose the claim is false. So let's make a messy drawing. Suppose the claim is false. Okay, I have enough space here. Let's suppose the claim is false. So there is an odd component of G minus B that looks like this. It meets both the shores. Okay? Suppose not. Let K be an odd component. of G minus the Dulmage-Mendelsohn barrier, right? Such that vertex set of K intersection X is not empty, and vertex set of K intersection X bar is also not empty. There is an odd component, so one of these two will be odd, the other one will be even. So I adjust notation so that this is odd and this is therefore even. Okay, so this is an odd set and this is an even set, and they are both non-empty. Yeah. The core is matching covered. So if I take any perfect matching of the core, that perfect matching basically extends to a perfect matching in the original graph. Right? Everybody agrees? The Dulmage-Mendelsohn barrier. So every perfect matching of the core extends to a perfect matching in the original graph. In fact, that doesn't even require Dulmage-Mendelsohn. That is in general true. Any perfect matching of the core, no, I need the factor critical. I need factor critical because in each odd component I need to complete it, and because I'm taking an edge with respect to a barrier, all the even components are anyways matchable. Right? In a matchable graph, you take a barrier, then the even components are anyways matchable. Yeah. Okay. So therefore, if I take a perfect matching of the core, I can extend it to perfect matching of the whole graph. Therefore, but observe that such a perfect matching will match some vertex of K into some vertex of the barrier. You all agree? Some vertex of K will have to be matched into some vertex of the barrier. That is true for any perfect matching of the graph G with respect to a barrier. Every odd component will have to use one vertex of the barrier and all the even components will be matched up, right? So therefore, but we know that the edges in the cut are actually not matchable in the original graph. So therefore, what can I say about B intersection X? In a perfect matching, this will be matched to some vertex in the barrier. Where will that vertex be? That's what I'm asking. That vertex will be here or will be there? It will have to be here. Is that correct? Let's just make sure. Yeah. So, why can't it be here? 1 second. I'm confused. So why can't this vertex of B be here and I match like this? Then the problem is, now I have an odd number of vertices here, an odd number of vertices here. So therefore I will have to use some edge like this. If this goes to the barrier, if some vertex from this part goes into the barrier and that vertex is an X bar, then I'll take a perfect matching running that edge, and now because there is an odd number of vertices after I match this vertex, I will have to match some vertex here into some vertex here. That's a contradiction because all edges in the cut are unmatchable in the original graph. Right? So the So the vertex that goes to the barrier, that barrier vertex has to be x in x. Yeah. So basically the point I'm making is that B intersection x is actually empty, non-empty. So this is my B intersection x. I don't know how much is in x bar. That part is not clear. And when I take a perfect matching, it should look like this. Is that correct? All right, let's see. I'm trying to see if there's another way to think about this. I know there is some edge here. Hi. Oh, there's a class here? Oh, sorry. Yeah, so let's complete this next time. We'll keep it as a TIY. Yeah. Yeah, sorry, I completely forgot about that. Yes.
This is the critical.
Yes, we should, but now there's a class, so we'll just complete it next time. Yeah, thank you. Yeah, sorry about that. Maybe next time on Thursdays, please remind me. Yeah, because I think on the other days there is no lecture after hours. Yeah, okay, thank you.